dribble it. So we're going to round people up. You're going to do it. Yeah, there is. Not that it does anything unless Sanjay switches on the sound of his so you can hear a nice echo from yourself.
Okay.
And, shouldn't happen.
Hi.
How are you?
There, give it a minute, there are at least 3 people coming.
Okay. Yeah, I just saw the school later. Yeah, it's more the activity, especially if you don't really care.
And also, walked around, I got back at 11:30 at night, and I'm walking on this road from my house towards my house.
When is this?
There's this kid.
Well, we're going to have, he's going to present some preliminary things next week. I mean, we have all the results that are kind of coming in now. He's not
So you go around scaring children.
It scares me too, you know, if I saw him in a little bit.
We don't say that.
There are two.
Sorry, shall we? All right, so good morning. Just a quick announcement before we start. So this afternoon we've got Chris's talk. It will be upstairs in 5:20 where we've been having the discussions. That's right?
Yes.
It's at 3. I think because of logistics, it's probably best if we don't try to have a discussion after, because Chris will obviously go on and on and on and on, and there will be questions after that, and questions to the questions and so on. So maybe we'll just keep that discussion going instead.
So you're saying I should just make a longer talk?
You can if you want, but we might just walk out. Right, so this morning we've got Tsvi Piran, and the title is up there, and so we're very pleased to have you here.
Okay. Good morning. So I'll talk about some work on the rate of short gamma ray burst and the implications to Newton star binary mergers. And this work was done with a lot of collaborators, but I want to stress here some students in postdoc, David Wonderman and Paz Binyamini, who were students in Jerusalem, Omer Bromberg, who is a postdoc at Jerusalem and now in Princeton, Simone, a postdoc also at Jerusalem and now at Tübingen, and Oleg Korobkin, who is at Stockholm, and Martin Obergaulinger, who was at the time at Jerusalem and now is working in Spain. So the outline of my talk, this is the outline of my talk. First, I'll talk about the relation between long and short gamma ray burst versus collapsars and non-collapsars. And it will be clear in a moment what I mean. Usually it's used to be in our concept there is sort of one-to-one connection between long gamma ray bursts and collapsars and short gamma ray bursts and maybe neutron star merger or another phenomenon. I want to show that this is not so simple. Then I'll talk about new estimate of the rate of non-collapsar short GRBs using all the data which is available today. And this is the result. This is the rate of short gamma ray burst. And then a few words about several implications, among them the rate of events detected by LIGO and Virgo, and the implications to nucleosynthesis, to our process nucleosynthesis. Now, a quick summary, so before you fall asleep, I'm fairly tired of the jet lag, so I don't know about you, before I fall asleep. So about 1/3 of Swift short GRBs, short, I mean less than 2 seconds, are collapsars. So this is about the ratio. 1/3 are not genuine short. The rate of non-collapsar short GRBs is 4.1. Actually, it should be plus or minus 2 per cubic gigaparsec per year. And this rate depends critically on the assumed minimal luminosity for this event. I'll talk about this later. With this rate, a LIGO detection rate is about 3 to 100 per year, or 0.1 to 3 coincided with a short gamma ray burst. But here we have some observational factor which may reduce this by a factor of at least 2 or maybe 10. A typical time delay of 3 gigayears after star formation for this non-collapsar short GRBs, which implies an initial separation, typical initial separation of 2 times 10 to the 11 centimeters. It seems as if this number is engraved into these systems. And with a beaming of about 30 and mass ejection of about 0.2 solar masses, then this rate is compatible with our process nucleosynthesis for heavy elements. Okay, so you all know that we see gamma ray bursts going on in the sky at a rate of about 1 per day. And they are divided to 2 groups, long and short. And this is the distribution of durations. And this is the number of bursts. So we can see here clearly 2 humps. And the separation, classical separation, which was based on BATSI data, was 2 seconds. And there is also some small but important difference in the properties of the long and the short bursts. They are very similar in almost every aspect, apart from the fact that the short ones, which you see here, are harder. This is the hardness ratio, which by this I mean the ratio of high energy photons to low energy photons. And you see that this ratio is slightly higher for the short gamma ray burst, and it is lower for the long gamma ray burst. So they are sometimes called soft long, and these are hard short bursts. And by now there are sort of 2 classical, there is understanding that there are 2 different origins, where for the long GRBs, the standard model is that these are taking place in a collapsar. And in a collapsar, a massive star collapses. It forms a central engine. The central engine, and I don't care, when I say collapsar, I don't care about what is really the central engine. In my mind, the central engine could be an accretion disk or a magnetar, or anything. I don't care exactly what. What I do care is that you have a star surrounding the central engine, and you have a jet that has to cross the star and penetrates out of the star. This is a key ingredient for the collapsar model, that you have a jet that has to go out of the star. There is direct evidence for this, and the direct evidence comes from the fact that we do see supernova associated with long gamma ray burst. I want to make a cautionary remark here that there's a lot been said about the fact that we see supernova associated with long gamma ray burst, but indeed we saw only 2 supernova associated with genuine long gamma ray burst. 4 or 5 other supernova are associated with low luminosity gamma ray burst, which are completely different objects. They are not formed by this mechanism at all. There is no jet there. It's impossible that there is a jet there. So there is a link, but the link is not as clear-cut as some people stress it. For the short GRBs, there is only indirect evidence coming from the positions of the short gamma ray bursts within galaxies, which, for example, this burst, this was the first short burst which was identified. It was within elliptical galaxy, so indicating that this is coming from an old population. So it's not associated with deaths of massive stars. Now, even so, I want to talk about short gamma ray bursts. I must say a few words about long gamma ray bursts so you'll understand where I'm coming from and why I claim that some of the short bursts that we see are collapsars. So This is again the collapsar model proposed by McFadden and Woosley in '98. And you have here a central engine somehow that forms and produces jet. And jet, this is from the first simulations of McFadden and Woosley. This is an artist concept how this will work out. And the main point here is that the jet has to do work to get out of the star. The jet has to make a hole in the star. And to make a hole in the star, you have to drill. And to drill, if you ever use the hand machine like this, you know that it takes two things, energy and time. And even if you use electric drill, then it also takes energy and time, but you don't feel it in your hand. And the point is that you have to take this into account. And only once the jet gets out of the star, we can produce somehow the emission at larger distances. So this is, for example, a jet simulation done by Martin Obergaulinger. And you see the jet getting out of the star. These jumps are because we are changing the scale. And this jet actually went out of the star. But in order for the jet to get out of the star, the engine has to operate here continuously during all the time that the jet was propagating out. And the jet we have to keep putting energy into the star. You can do something else. You can do another simulation. And now you can stop the engine after about 2 seconds. And this is what happens. The jet disappears. The jet just puts all its energy into the star. The energy is dissipated. This will not produce a regular GRB. It may and most likely produce this low luminosity GRBs that I mentioned, but this is, as I said, it's a completely different process. It's not produced by a jet that gets out of the star. So this is the key point here. And what we have done is we have calculated both first analytically and compared it with numerical estimate, the time that it takes for the jet to break out. And this is how it scales. Depends on the luminosity of the gamma ray burst, on the opening angle, on the size of the star, and on the mass of the star. But for typical values, this is about 15 seconds. So it takes about 15 seconds for a regular jet to get out of the star. And this is sort of surprising. If you look at the size, it means that the jet is propagating not at the speed of light. It's propagating at about 0.1 to 0.2 of the speed of light. It's not, even so you start with a relativistic jet, it becomes only mildly relativistic or subrelativistic within the star. The head becomes slower, and only when it gets out, it becomes relativistic again. So this is important, and as I mentioned before, the engine must be active until the jet breaks out. This means that we have a very simple arithmetic problem. If this is the total time that the engine operates, then it will be divided to 2 parts, breakout time and T90. This is the T90. This will correspond to the observed gamma ray burst, and this will correspond to the time that it took the jet to get out. And if you remember that this is 15 seconds, then the typical time scale of this T90 is about 10, 20, 30 seconds. So the 2 times are comparable, or actually, so it's not negligible part. And this means that in many cases, actually, the breakout time will be longer than the engine operating time. And in this case, we'll have this failed burst, the failed jets. And this means that there will be also many cases in which the two times will be almost comparable. And then we'll have a very short burst coming from a collapsar. Now, you can do the statistics here. It's very simple, but I'll not try to bother you with the equations. If you have such a system that T90 is TE minus TB, and as long as the two things are not correlated, and there is no reason for them to be correlated because the breakout time depends on the global properties of the star, how large is the star, and so on. And this depends on the intrinsic properties of the star. There is no time for feedback here. So as time as they are not propagated, and as time is this is not too small, then we have the following feature. that if we look at the expected durations distribution of durations and number of events, we expect a plateau. And the plateau should last until until T90 is over the order of the breakout time. So we'll expect a plateau at short durations, and then something will happen which, depending on how this engine operating time distribution behave, it can go up, it can go down, but we definitely expect plateau at durations which are much shorter than the breakout time. Now, the breakout time is 15 seconds, so we expect a plateau. This is an immediate prediction of this model, a plateau at durations of at less than the breakout time, which I remind you is of order of 15 seconds. Now, historically, from a personal point of view, what happened is that we came out with these calculations and with these arguments, and we didn't notice that until one of us said, oh, but it's impossible. Your result, something must be wrong in your result, because you expect this plateau, and we don't see this plateau in the model, so something is wrong. And why is so that we don't see the plateau? Because if you look at this diagram, you don't see a plateau. So we said yes, but this is d log n by dt. This is what is traditionally plotted. If you plot it at the n by dt, which is what we calculated, you see this plateau. And you see this plateau in the three different duration distributions of, this is Batsy, this is Swift, and this is Fermi. So you see this plateau. And in my mind, this is another a strong argument in favor of the collapsar model, or basically in favor of a model which has such a relationship in it. And this relationship arises naturally in the collapsar model. So in my mind, it's a strong argument in favor of something like the collapsar model operating in long duration GRBs. Stronger in my mind than the other evidence that we have for this model. Now, of course, the plateau does not remain forever, but we can test a few things. If you remember, I mentioned that the short non-collapsar GRBs are harder. So we can do the following exercise. We can take the Batsy data, and we can introduce a cutoff and eliminate the hard part of the distribution. So we can take only half of the distribution. What we expect in this case that the plateau will go lower to shorter durations, because these are this other population. These are the short bursts which do not participate in this game. They are not collapsars, so they do not obey this rule. But if we go to softer distribution, then we expect it to be the plateau to be longer, and this is exactly what we see here, and the plateau is longer. And okay, and this is this indication here. Okay, so now, so these are the short non-collapsars, and you see here that the short non-collapsars dominate the distribution up to different durations in the different detectors. And this is natural and expected because the different detectors have different response, have different energy response. So Swift is a much softer window. And if Swift is a much softer window, you expect that Swift will detect more long bursts than short bursts. And indeed, it detects the ratio of long to short in Swift is different. So the plateau really goes much down to shorter durations in Swift. Okay, and this is now a movie that demonstrates what is happening here. So what I'm doing is I'm gradually reducing the threshold for the energy. And when I reduce it, you see that as the system becomes softer and softer, the plateau becomes more and more prominent. until, of course, it disappears because there are no more bursts. So this is the summary of the situation, and we can do further. We can divide the distribution to three energy bands or three hardness bands, and do fits to these distributions, and we can estimate from this what is now the likelihood that we see a given burst. So what is the likelihood that this burst is short or collapsar or non-collapsar? So this is now for Swift, and you see that, as I mentioned before, that the plateau ends here at about 0.7 seconds. So there are many more. So burst GRBs, Swift GRBs with T90 larger than 7 seconds are most likely not genuine short. They are most likely collapsers. Okay, and then we can try to calculate the fraction, and we can calculate the fraction of short GRBs in each of the detectors as function of their hardness and as a function of their duration. Okay, so now, given this data, given this information, we continue and we make a jump, and we want to estimate now the rate of non-collapsar GRBs. We are interested now in the short GRBs, but only in the ones that are non-collapsars. So what do? We take the following sample. We take the BATC, all the BATC short burst. BATC burst with less than 2 seconds is more than 90% being non-collapsar, so it is okay. The same thing for Swift, for Fermi. We take these two populations, but the problem is that these two populations have only peak fluxes. We don't know the position, and if you have only the peak flux, it's much more difficult to determine what is the rate and what is the luminosity, because there is a convolution, and you have to assume something about one of the two functions, either the luminosity function or the rate, to determine the other. You cannot determine the two functions independently. So this by itself is not enough to determine the rate. And but luckily we have now Swift. So we take Swift short burst with redshift and but we also take only the ones which have high probability of being non-collapsars. So we look at this table here. When we take only the burst, depending on the hardness of the burst and the duration, we assign probability, and we make a subsample out of about 20 short bursts on Swift with genuine redshift and therefore luminosity measurement. We take only 12, which are likely to be non-collapsars, and we add this into the analysis with this. And now, what do? We assume we take some two models of the star formation rate. These are different models of the star formation rate, but we take as our canonical one this one and this one as two options. And we now assume that the rate of the short burst is some convolution of the star formation rate and a delay rate. And so this is the delay function, which left have to be determined. So we take various different delay functions and assume that the rate of short GRBs is proportional to this integral of how much star formation rate happened from Z to infinity, but then was weighted by different delay time between the burst and between the star formation and the burst. Now we assume that this is the shape of the luminosity function. It's a broken power law with a critical break at L star. But we also assume that there is a minimal minimal luminosity. And we must assume this because we don't know what's going on here, because we haven't seen burst below some given luminosity. So we assume that there is a break here And for simplicity, we take a sharp break. So this is the luminosity function that we fit. And now we have the following parameters. We have these two indices here of the power law, L star, which is the break of this luminosity function. And we also have this functional form here, which is the time delay. And we take two functional forms. We have one functional form as that we assume that this is a power law in delay time, t to the tau to the minus alpha, with alpha is some unknown power. So we have one parameter, then the power law delay time. Or alternatively, we assume that this is a log normal distribution, and then we have two parameters, the typical duration, typical delay, and the spread around this delay. And then what we do is a global maximum likelihood, in which we put here the probability to get pi is the observed flux. So for Batsy, we have only the observed flux. So we calculate what is the likelihood to have the observed fluxes. For Fermi, we have also just observed flux. So we calculate what's the likelihood to have this observed flux. And for Swift, we have the redshift and therefore also the luminosity. So we then plug this into our model for our to the luminosity function and for the model for the rate and calculate the probability. And we have this weighted probability. And this is, for example, how the result look. This is two fits that we get to the data, and the two fits are for the two different star formation rates that I mentioned before. This is the Batsy peak flux distribution of short GRBs, and this is the fit that is obtained using our best fit parameters. More interesting is to see what's happening with Swift. For Swift, we have both the distribution of peak luminosity and redshift. And so these are the different fits that we get, and they are all statistically consistent with the data. So for the different models, and I will not bother you with the different details of the different models, but for the different models, for each one we have rho 0, which is the current rate, alpha and beta, which are the power laws of the luminosity function. You see, these are actually quite constant. They almost do not depend on the model. L star, the typical break energy, which is also fairly constant. And then the time delay, typical time delay in giga years, the spread around this time delay. And if we have a power law model, then what is the index of the power law? If we assume a logarithmic, constant logarithmic distribution of initial separation, we expect here the power to be 1. And this value of 1 is consistent. But systematically, these fits, which assume a power law distribution of delay time, are worse than these fits, which assume a log normal distributions. And the best fit for the log normal distribution is actually 0 widths. So it actually, the result that we get is a very narrow distribution. Yes?
So here, so you use the entire short GRB sample or the 1/3 of the short?
This is for the reduced. These results are for the reduced sample. I will tell you in a second what happens if we use the full sample.
And also for Batsy and Fermi?
No, for Batsy and Fermi, there are so many bursts, and since we have only peak fluxes, for Batsy and Fermi we use all the short bursts less than 2 seconds, because all of them are more than at 90% likelihood genuine non-collapsers. So for them, we use the whole sample. Actually, here, what you can do in Batsy and Fermi, in fact, you can push it a little bit higher. You can push it even to 3 or 4 seconds, but there is no need because the sample is large enough. We will not gain statistically if we increase the sample. But here, for this analysis, we used only the burst which has, I think, more than 60 or 70% to be genuine collapsers, and so non-collapsers. So this is only for the subsample of the data.
So in principle, also do the flux distribution of the Swift sample as well.
But
another criteria.
But there is no need. You can add the whole full flux distribution, but you don't gain much from this because already here you have so many more bursts than here, then this will not give you much more. You're right. In principle, we could have multiplied here by Swift, short Swift with no redshift. You will get another 20 or 30 bursts.
Or with redshift, you just do flux. With redshift, it's fine. You just do flux instead of luminosity. Now, all the short TRBs.
If you just have flux without redshift, you cannot do this exercise. To do this exercise, you must have this. Without this part, without this group.
No, I mean, you keep this one, but add one more term for the Swift flux.
But there is not. You can add it, but you will not gain much from it, because you already have about 600 points here, and if I remember correctly, 150 or 200 points here. So you will not get much from adding another component with another 20. You can do it, but there is no need to do it. This is the intrinsic redshift distribution, and it's sort of comforting to know that regardless of the star formation rate that you take, you get more or less the same basic distribution of intrinsic final distribution of the rate of short GRBs. There is a delay after the peak of the star formation rate is around 2 to 2.5 or 3, depending on which model you take. There is a delay after this peak. But because there is a peak here in the history of the star formation in the universe, this is translated into peak in the rate of short gamma ray bursts. And actually, there were more short gamma ray bursts in the past than now. The peak was around redshift 1. So what happens is that if you change the star formation model, then this will effectively give you a different delay time distribution, which will compensate and will bring you back to more or less the same distribution.
So is the assumption that the redshift distribution is an unbiased tracer?
Yes, without this we
Sure,
cannot.
yeah,
Yes, we assume that the data is tracing what is. Well, it takes one thing. It takes into account. It takes into account that if you have a weaker burst, it will be detected only for shorter distances. This is built into the model. If there are other biases, then this does not take it into account. So this intrinsic bias is taken into account, but no other biases. So for example, if it is easier to detect redshift in different ranges and so on, then it will change this fact. Okay. Now about the time delay. So this is the time delay distribution for the long normal distribution. So this is the width of the delay, and this is the delay time. And the difference here is for two different star formation rates. This is the more reliable one, so I'll focus on this one, the more reliable star formation rate. This is just an example what happens if we change the star formation rate. The peak here is about 2.9 gigahertz delay. You see that the results are consistent with 0 width for the time delay. So everything is just 2.9. And you see the contours here. And you can say that you can get a width here of maybe half or a gigayear around this value, but not much larger than that. Okay, so this is this distribution. And now about collapsers and non-collapsers. Now we did one more exercise. We took now the whole sample. So if you remember, I intentionally took only only 2/3 of the short Swift GRBs. This one's the one that were assumed to follow, to be a genuine non-collapsar. But now I take everything and say, okay, I take everything, but I'll also allow for something else. I am introducing one more parameter, which is the fraction that follow the star formation and the fraction that doesn't follow the star formation. For the fraction that doesn't follow the star formation, I use the same exercise as before. I allow for time delay. For the fraction that follow the star formation, their rate is dictated by the star formation model. And again, I do this for 2 star formation rate. And now I have plots for these 2 parameters. This is the time delay. And this is the delay. And this is the fraction of the star that follow the star formation. Now, the bottom line here is when I take only the first group that I took. And as a consistency check, the best fit value for this group is 0 following the star formation, and everything with a time delay of 2.9, or here it was 3.9 gigayears, consistently with the result that we got before. So when I add this parameter to the genuine collapsers, nothing changes. When I now add this parameter but use it on the full sample, I get the following result, that it tells me that about 1/3 of the bursts should follow the star formation rate. And then for the rest, the delay is the same as I had before. Now I have here 2 lines, because in this full sample there is 1 burst for which the redshift is not clear. It's either 0.7 or 1.8. So depending on whether you put 0.7 or 1.8, you get these 2 curves. But basically the result is the same, that when you introduce the full sample, you get automatically a group that follow the star formation rate, more or less at the same size of the ratio of this fraction. The fraction was about 6 to 12 or something like this. So you get it about 1/3 from this category, or 1/3. Now, there are 2 to be honest, you can have 2 interpretations of this result. You can say, okay, what I'm saying makes sense. I've really confirmed that 1/3 are genuine collapsers and 2/3 are non-collapsers. You can also say, well, forget about everything. Everything is coming from non-collapsers, in spite of what I said before. But for some reason, there are 2 populations within the short GRBs, which are non-collapsers. Both of them are non-collapsers, but some of them follow the star formation, some of them do not follow the star formation rate. Why does this has to be correlated with the hardness distribution and with other factors? I don't know, but this is a possible interpretation of the data. It's not my favorite one, of course.
But this is exactly the situation for type 1a supernovae, right? That there is a 2-component, there is a component that follows the star formation rate, and there is a delayed component. And there are correlations between the intrinsic properties of the supernovae and these 2 populations. The ones that have a longer delay time are intrinsically lower luminosity than the ones that have a shorter delay time. So I'm not saying that it has to be the same. I'm saying there is another astrophysical system where exactly the same thing is the case, and there are indeed correlations between the properties of the events and the delays.
As I said, there are 2 possible interpretations of this result. One interpretation was that we predicted, based on these curves of the duration curves and the hardness curve, that about 1/3 of the short bursts are coming from collapsers, and as collapsers they should follow the star formation rate. And you reproduce this, and you can also say this. Both of them are non-collapsers, and for some reason 1/3 of the non-collapsers do not follow the star formation rate, and they are also harder, and another fraction is so on. Then you'll have problems with explaining the plateau, but that's a different story. Okay, so let me go now to some of the implications.
A quick question before you move
Yeah.
on. I don't know if you're going to talk about it. If not, I'll add it to my talk tomorrow. But there is a corollary of all this, which is the distribution of host galaxy types in the context of this model, and how that should be distributed relative to what we observed. And there is also the idea that if the events with the longer durations are indeed collapsars, then they should have supernova associations. Just
I'm not going to talk about
okay,
it.
so I'll talk about this.
We can. I'm not going to talk about the hosts. Okay. Yeah, well, actually, I'll make only one remark, but I'm not. Maybe I'll make this as a remark during your talk tomorrow, because what we have found, actually, it was not necessarily in your work. It was most in some other people's work. That if you take that, some people have taken subsamples of short GRBs and tried to learn on properties of them and came with conclusions about the properties of host galaxies or so on. But in at least in few cases that we know, the subsample was completely, because of some unlucky reasons, was completely dominated by what we considered was as collapsers. And so people came with strange conclusions about the populations of hosts or properties of hosts of short GRBs, where these conclusions, they show that they are incompatible with models of mergers in some cases, but this was just because of unlucky reason they had a subsample which was completely dominated by this subgroup which is collapsers. But this is not necessarily your work. It's other. I may mention it tomorrow when you discuss it. Now let me go to a very important issue with the which comes with the determining the rate of these events. This is a figure which contains two bits of data. First of all, this is our results. And the error bars are the statistical error bars that we get in this analysis for the two different models that we have, the two different star formation rates, and this is the width around this. And this is now the local rate of short gamma ray burst. And we are using as a canonical value the rate assuming that the minimal luminosity is 5 times 10 to the 49. So it's somewhere here. This is 4 events per cubic gigaparsec per year. Now, this rate has some width around it, which is plus or minus about 2. But much more important is the deviation due to the assumed lower limit of the luminosity of these events, because if you look at the luminosity function increases steeply when you decrease the rate, when you decrease the luminosity of the events. So if you go to sufficiently low luminosity, you can increase this effective number by a value which is much larger than the statistical error here. So why did we use 5 times 10 to the 49? Because this is the lowest observed luminosity of short GRBs which was observed so far. This is the lowest observed peak luminosity. If you observe a lower one, we will have to push it to low energy. So this is what we observed. So this is why our value is roughly here. The other lines here, by the way, are results from different works that have done have done the same analysis. Some of them are slightly larger than us by typically a factor of about 1.5. This is because they use the whole non-collapsal sample and not the whole short GRB sample and not the reduced sample. This reduced the rate by a factor of about 2/3. And all these works make very different assumptions. And these lines also indicate what is the minimal energy assumed in each one of these works, which is a very important factor. So when you try to get rates from this, you have to be very careful because of this energy dependence. And this is why when I quote rates, actually the rate may be much more uncertain than this uncertainty here, the statistical uncertainty.
So all the data points are from different groups?
These are all the different groups that have.
And some of them have very small error bars, like the.
This is the quoted error bars of the different groups, not my error bars. So this is different works. I do not remember which one is which, but these are the different works that people have posted. All the works on short GRBs which were done in the past can be found on this diagram.
You claim that the actual rate would only be higher than than what you assume, right? I mean, you would say what you're finding is a lower limit.
What I would say is that what I found is a lower limit, and it will be higher if there are lower luminosity if there are lower luminosity ones, which is consistent with the fact, because there could be lower luminosity one and we wouldn't observe them. This is consistent with observation. So this can be, you can think about it as a lower limit if you wish. So the summary of this is the rate is 4 plus or minus 2. This gives a typical spiral in-phase of, actually it's written here 2.5, it should be 2.9. And this is this value here. It is consistent with a merger rate of about 200 per cubic gigaparsec year for a beaming factor of 30. And this is consistent with rate estimate based on galactic neutron stars, which I'll talk about say a few words about them now. So this is the neutron star, binary neutron star sample in the galaxy. And this is the masses. And what you see here is the current separation, and this is the separation at burst taken using the age of the pulsar. So this is taking the age when the system was born. It was born here, and it shrunk from here to there. This is the binary pulsar, the double pulsar, and it's simply fairly short lifetime, so it didn't move at all. And this is this line, which corresponds to this time scale that I said before, 2.9 gigayears. And everything here above here will be probably, it will be too long for this to merge in Hubble time. Now, you can also plot this as function of the eccentricity. And this is one group here with higher eccentricity, these guys with very high eccentricity, and so on. But these guys are all here are with fairly low eccentricity. And particularly important is this guy here. This is the double pulsar. And here I want to stress a completely different piece of work. The argument that we had already in 2005, that the double pulsar was not born in a regular supernova. And one can see this, that the second pulsar in the double pulsar was not born in a regular supernova from the kinematic properties of the system. The system is moving almost on a circular orbit. The ellipticity is very small. It is fairly nearby. It is in the galactic plane. The fact that it is in the galactic plane suggested that it does not have a large velocity, and this put constraint on the possible kick velocity that the system could have. So within about 2 weeks, after this pulsar was discovered, we suggested that this was not born by a regular supernova, but by a different channel, and the progenitor mass was about 1.5 solar masses. This is the mass of the progenitor, and it is between 1.47 to 1.54 solar masses. And the ejected masses that we initially suggested was somewhere between 0 to 2.1. And we had a prediction, and the prediction was that this system will not be moving. There will be no center of mass motion. Now we sent it to Nature, and we got the most interesting remark. It was not even the referees, it was Leslie. So he wrote, Tsvi, you have a very nice prediction, and you write in the paper that this can be tested within a year. Why won't we wait a year to see if your prediction is correct and publish the paper? Now, the story was funny because the standard model predicted large proper motion, and there was a wrong discovery of large proper motion. So we were disappointed and surprised, but this wrong discovery turned out to be wrong. This measurement was turned out to be wrong, and this object is standing still. The velocity is less than 10 kilometers per second, so it's almost not moving. So now we have much more constraint, and there are additional constraint that we know that at least one of the spins of one of the spins of the system is tilted, by one of the spins is completely aligned with the orbital period. The other one is at 45 degrees, or actually 135 degrees, but it doesn't matter. So, so there is information on the spins, and you can factor in the information on the spin also. And we get a very precise estimate of what happened there. The progenitor mass was 1.5 solar masses. It's like a white dwarf with some atmosphere. And somehow this thing collapsed, ejecting 0.1 to 0.15 solar masses, and also its regular matter, and about 0.15 solar masses as neutrinos, getting to the 1.25 solar masses that we obtain. Now, why is this important? This is very important because, so this more recent analysis, including the spins, was done here in this paper by Simone Daloso and Nir Shaviv. Why is this important? This is important because this is a very different formation channel for this object. And this object is, dominates the estimate of the rates of neutron star mergers based on the existing population. And this formation channel is not included in the usual population synthesis models. So this is very important because it may tell us that the usual population synthesis models have something very important missing there. And moreover than that, it seems to me that this whole group with low eccentricity and low masses was probably formed by this channel. So I would say that not only this is an important group, but it may be the dominant group for the population that we see today. And there is a different group altogether with these high eccentricity ones. And this will be important because they can, these guys will never merge. Will never. They'll never merge on a Hubble timescale. I mean, they are much too far away, but they also have high ellipticity. And these guys were probably the guys who were formed in the standard scenario,
This is an accretion. The expectation is that there was some kind of accretion event that drove this over?
No,
what is it accretion
no.
event?
This is exactly why this is very puzzling, because it cannot be accretion-induced collapse because the other guy is already a neutron star.
Yeah.
So if the other guy is already a neutron star, it cannot be accretion-induced collapse. What we expect is that this is that this is somehow. Oops.
So I was assuming it was just like a low mass star that these stars go from this range where they're deciding whether they want to be a collapse and become a neutron star versus become a white dwarf. You could easily have a phase where you eject a lot of the mass, prior to collapse.
Exactly, and more than that, if you look at this separation,
Yeah.
it's 2 times 10 to the 11. If you look at these guys were originally 8 solar masses. This is less than the original separation between the two stars. The two stars must have gone common envelope phase. And my guess is that somehow this common envelope phase has something built in there that brings them into they eject a lot of mass and ends at around 2 times 10 to the 11. How it is doing, why it is doing it, I don't know. But from these figures, my guess it's something in the common envelope phase is leading the system to this configuration of separation of about 2 times 10 to 11. And then, in these cases, it leaves something which is like a white dwarf with an envelope, with a tiny envelope. It can exist for a while, and then it collapses and ejects some excess mass and happen. How this is working, I do not know, but it's not accretion-induced collapse because there is nothing to accrete from. Yes.
May
May I comment? So I think 2 weeks ago we had already some discussion about this system. So the thing, and I think Nomoto showed these progenitors in this talk, that around 10 solar masses, the envelope of the star is very light. So when you do the corpuscular simulation for these models, you basically have prompt explosions. So no SASI, no ballistics. So these models basically don't get any kick. So you can form, I mean, around 10 solar masses, you can form neutron stars with no kicks, basically. So this is possible.
But kinematically, if you're in a binary and you eject more than this amount, more than this very small amount of mass, you must get.
Yeah, so the kick is 2 mechanisms. There's the asymmetric and the explosion, but then there's just losing the matter in a binary gives you a kick. And you're saying I can't even lose that much matter because it's not moving at all.
Yes, I mean, this system is actually, in this system, in this recent work, which I mentioned here, we even showed, we even showed